All right, so welcome to the Caffeinated Gopher's Guide to Language Runtimes WebAssembly Edition. So, my name is Edoardo Vacchi. I did a bunch of stuff before this, but in the last year I've been working on a WebAssembly runtime at this company called Tetrit. It's called Waziro. I'm going to tell you a little bit about that. Waziro, it's a WebAssembly runtime that was originally developed by coworker Takeshi. And the reason was that at the time, all WebAssembly runtime were native libraries. So why do we care? I'm going to explain that later. Then later in 2021, they decided at Tetrit to sponsor the project, and that's why I'm working on it. But why does this, what does this have to do with us? The timer hasn't really started, guys. Please. Thank you. All right, so thanks. So we are here to answer this question. What do Java, Go, WASM, and GraalVM Native Image have in common? So we're trying to answer that. This is more or less the way we're going to do it. I'm going to give you a little introduction to WebAssembly. Then we're going to talk a little bit about Go versus Java, how they relate to each other. Apparently, I mean, they may not look like they're related, but they actually are in a way. I'm going to tell you a little bit about GraalVM Native Image, about WebAssembly as a compilation target, and this would be for running Go and Java on top of WebAssembly, and then we're going to see how Go relates to Java and vice versa when it comes to running Go and Java on top of WebAssembly. And then we're going to draw some conclusions. So I'm going to start giving you some very quick and short introduction to WebAssembly. So as Java developers, we hear about WebAssembly and we think, is this the JVM, right? So the past year, I've been going around with some presentation trying to convince people that they're not exactly the same thing, even though they're definitely similar to each other in some ways, but they're also dissimilar in some ways. So WebAssembly was born out of a need. So we were running JavaScript in web browsers, and people started to treat JavaScript as a compilation target. However, it was not great as a compilation target. It wasn't supposed to be a compilation target, and we were using it anyway. So people started to think, what if we can leverage the JavaScript runtimes that we already have in our browsers and instead provide something that it's a proper compilation target, and then leverage these runtimes to do their work. And that's how essentially WebAssembly was born, and why we wanted it in the first place. So inside the browser, you might even be using it without realizing. Games that run in the browser are using WebAssembly. Google Earth is already using WebAssembly, and part of the Google Docs suite is using already WebAssembly. So probably some of the web applications that you normally use are already using WebAssembly without you even realizing. But I'm not here to talk about WebAssembly inside the browser. That already works, and I mean, that's a use case that we already are familiar with in a way. So WebAssembly is kind of bare bone. It's a very tiny VM. It's minimal. And then because it's minimal, it's very easy to embed. It's very fast to boot. It's much smaller than a complete Java runtime environment. And that makes it very interesting to provide to end users software extensions, because you can embed it inside other environments. For instance, another thing that it lacks and that makes it so small is that it comes with no standard library. So it's kind of like if we have the JVM, all of that stack is the entire JDK, then there's the JRE, the runtime environment, which is basically the VM plus all the libraries. And it's essentially our WebAssembly runtime is here. It's just a bit that allows to execute bytecode. So if you can just run bytecode, all you have is a fancy calculator. So how can you interact with the environment? When there are some things, there's a sort of a standard layer of syscall that's called WASI that provides a thin layer of abstraction on top of the operating systems that is generally available when you run outside the browser. And well, just keep this in mind. It's not important, but I mean, that's how it will work. So there's a number of WebAssembly runtimes. I already mentioned there's the browsers, there's Node.js, obviously, which is V8, and it runs JavaScript and WebAssembly. But there are also WebAssembly runtimes that are born and only run WebAssembly. That one makes them so tiny and easy to embed. They're written in generally in the C, Rust, C++. So they're native libraries. You can link them in your software with some downsides. The good thing is this can run essentially in any application. They can be embedded in any application. And that makes it possible, as compared to larger runtimes such as the JVM, to provide extensibility to end users without paying too high a cost. So there are, for instance, some platforms, some applications that already do that. For instance, Red Panda is a re-implementation of the Kafka protocol, so completely, essentially a drop-in replacement for Kafka, but it's written in C++. And as opposed to Kafka, it provides users the capability to run data transformation in the core, inside the broker. And the way it does that in a safe way, it's by using WebAssembly. Another piece of software that uses WebAssembly as a way to allow end users to do extensibility, it's Envoy, which is one of the components at the core of Tetrate products. Envoy is a network proxy that allows you to intercept requests and responses and rewrite them, reroute them. And the way it does that is by the way of filters. These filters can be built in, can be written using the native language, C++, or they can be written using a scripting language, in our case, Lua. Now, the problem with the scripting language is that you have to learn that particular scripting language, while WebAssembly, as I mentioned earlier, it's a proper compilation target, and it can be targeted by any compiler that has support for it. So, in theory, what you get is you still get sandboxed execution because it's not just linking directly to the main executable. You have you have dynamic loading because you can dynamically load these binary modules that you generate with WebAssembly, and you can pick your own language. So that's pretty cool. One of the languages that higher level languages that you can use to target WebAssembly is Go, through this flavor of the Go language that's called TinyGo. There are other languages that are able to target WebAssembly. There's Rust, there's C, there's C++, and there's a growing number of languages, including Python, Ruby. And so TinyGo is particularly suitable. It was one of the first flavor of the Go language that supported this, because, especially running outside the browser. TinyGo is born to target tiny devices, embedded devices, and it produces especially small binaries. That's why it's also cool and good to use for WebAssembly. So that's already working. WebAssembly allows your users essentially to write software extensions using their favorite language and running in a sandboxed environment. So you can use Go. Now, the question could be, the rest of the talk is we'll be trying to answer two questions. Can you run Go and Java on WASM? And can you run WASM and Go, can you run WASM on Go and Java? So I already mentioned that essentially Go can be run on top of WebAssembly. So the question is kind of like, what about Java? So let's see the differences and similarities between Go and Java. So Go and Java are kind of dissimilar from a perspective of how you write code, for instance. Java is an object-oriented language, and Go, well, in a way it is, but not in the same way. So Java has classes and has interfaces. Go doesn't really have classes. It has another form of inheritance. You can embed structs inside of other structs. It comes with interfaces, but they do not work the same way Java interfaces work. The style in which we write Go code tends to promote shallow type hierarchies, while Java code in general, especially older code, tend to be based on deep type hierarchies, so very, very deep type hierarchies. And then in Go, you tend to use libraries, while in Java, you tend to use frameworks. So kind of larger body of dependencies. So that's for code style. What about the runtime? So in Go, you compile your code to a native executable, generally a self-contained executable, a static binary, which means that you can transport one single binary everywhere and it will run, provided that it's compiled for the right platform. The good thing is obviously, the thing you might wonder, right, if you target the right platform, what about cross-compilation? What about targeting multiple platforms? The good thing about the Go compiler is that it is able to produce binaries for many different architecture. I can cross-compile from my Apple Silicon M1, I can compile, which is ARM, I can compile Intel, and target Windows as a platform. So I can basically compile for all the platforms that Go compiler supports, which are pretty quite a few. Obviously, Java takes a different approach, but it's still obviously portable. It's a bytecode target, so you compile once, and then you can run everywhere, right? Provided that you have the runtime for that specific platform. Another thing that is different on the Java platform is that you do dynamic linking. So essentially, you load classes dynamically at runtime. And it's a thing that you don't do in Go because you produce static binaries. Another way in the way you develop code using Go and Java is that Go shares libraries as source code, while with Java we share bytecode directly. So the cool thing is that still Go, it's pretty fast as a compiler. You wouldn't expect that, but it has some aggressive caching going on that makes the compiler super fast. Sometimes I would say even faster than some Java code bases. So that's pretty impressive. So I mentioned dynamic linking. This is a defining feature of the JVM in a way. Essentially, even before you reach, let's say that you're running some framework, so your application initialization is here with all your business logic. Even before you reach to that point, you have to reach your static void main, and then between your main application code and your static void main, there's all the potential framework initialization. So before you actually get to actually doing some useful stuff, there's a bunch of class loader involved. This class loader, in turn, would load about 500 classes even before they reach the static void main, and in turn, every class has a little bit of code that has to be executed in order for the class to be initialized, and that's called static initializers. And they're essentially in these 500 classes, there are about 160 static initializers to be run. And obviously, these numbers grow as the number of classes and the number of libraries grow. So there's a bunch of stuff, and that's what makes sometimes the boot up time for a Java application kind of slow. There's a lot of stuff going on there. So essentially, dynamic loading is a defining feature of the JVM, to the point that people say that a JVM without dynamic loading is not really a JVM. I'm going to get back to this later. Just keep it in mind. So I said a lot of things that are different about Go and Java, but I want to say that, so my point is that actually they're kind of similar. So in which ways are they similar? They have somewhat large runtimes. They both have somewhat large opinionated runtimes, especially when it comes to managing memory. They both are garbage collected runtimes. So your code is safe because there's no way to access invalid memory, for instance, and crash and tear down your entire application in a bad way. There's null pointers, but that's not as bad as SIG-SEG. So there's Go routines on Go. And Go routines are essentially an abstraction over threads. And now in Java, we have virtual threads, which are kind of the same thing. But even before we had virtual threads, we had ways with thread pools and executors to run tasks on top of a fixed number of threads. So we had that in a way. In fact, that's how essentially virtual threads work even today. So the runtime is so opinionated that it's not really meant to be embedded inside another application. You can do it, but generally people don't do it. Oh, yeah, another thing that they share now, thanks to Native Image, GraalVM Native Image, is that now you can also build static executables for Java as well. Okay, I mentioned that the runtime is not really meant to be embedded. Put a pin on that. We're going to come back to that. So the question whether we're trying to answer is, can you run Go and Java on WebAssembly? So this, in a way, is can be formulated in a different way. Can you write software extension in Java and Go? As I mentioned, these are somewhat large language runtimes. So do you really want to create shared libraries using Java and Go? Generally, people don't do that. You don't create DLLs and shared object files using Java or Go. Well, in Go, you can do it, but people generally don't do it. You usually use other languages if you want to do that. In Java, you really aren't able to create DLLs unless you use GraalVM Native Image. But it turns out, statistically, people tend not to do that either. So it's not one of the features that people actually use the most in Native Image, even though you can do that. So, yeah. Now, why did I mention software extension, native software extensions in the context of WebAssembly? Because WebAssembly behaves a lot like a native target. In fact, most of the languages that are able to support WebAssembly are languages that normally target native executables. They generate native executables. So for instance, C and C++ has support for WebAssembly, through Clang. Rust supports WebAssembly, excellent support for WebAssembly. Zig, TinyGo already mentioned, it's based on LLVM. All of these languages actually have an implementation that uses LLVM, which is a tool chain for essentially building compilers. And LLVM, one of the things about LLVM is that you can target this intermediate representation that they provide, and by doing so, you're able to use the LLVM backends for multiple operating system and architectures to support all of these architectures and operating system without doing too much work. So for instance, you can target x86, you can target ARM, you can target RISC-V, and you can also target WebAssembly. In what ways is WebAssembly similar to a native target? But one thing that makes it very different from the Java bytecode is that it doesn't provide, or at least it used not to provide, automatic memory management. Instead, it provided a linear memory, which is essentially a byte array, which it's an abstraction of our native memory, in which you can write and also allocate data and deallocate memory, just like you would do on a native target. So essentially, you do manual allocations, like what we call off. It's like if it were a JVM only with off-heap memories, what we call off-heap in the JVM terms. There's also now a GC spec. I'm going to tell you a little bit about that later, but that's something that is relatively recent. So that's why I wanted to talk to you a little bit about GraalVM Native Image. So compilers, how do they work? So the way compiler usually works, obviously, they translate code from some source code into native code, and that's all right. But what they also do is to drop all of the code that is unreachable or is useless so that it doesn't end up in the final binary. Otherwise, you will get a super large binary. So this is why Go is in a better position to target WebAssembly, because they already have a compiler that behaves this way. So what we do usually in Java is compiling our source code into bytecode, and then we just use that. TinyGo is especially suitable because it produces smaller executables, so it's also one of the reasons why it's good to target WebAssembly. So what about Java? Well, approach for Java could be just take all of your libraries, all of your JDK, and compile everything to native. Obviously, this will generate huge binaries, which are not useful neither as a native target, neither as a native binary, and obviously not as a WebAssembly binary. So instead of doing this, what you can do is keep the code you really use. That's nice. Easy to say, but is it that easy? Well, we already mentioned this problem, right? We have a lot of class loading going on at runtime, and this is normally how we write code on the JVM. So there's no real way to know beforehand what kind of code we're going to load at runtime. And even apparently harmless code such as this one, that just does system out println, right? This is a hello world. Does a bunch of different things, and there's a lot of stuff going on here. There's a method invocation over a subtype of up to stream. There's a field resolution going on, and that field is a static field of a class. So that class has to be initialized, and so that field has to be initialized. So we have to run the static initializer for that class, and in turn, in order to initialize that field, we have to load other classes, initialize those classes, and so on and so forth. So this looks like harmless code, but it does a whole bunch of stuff. So in Java, dynamic loading is essential. So how does GraalVM solve the problem? In a very clever way. Unless you have never attended GraalVM, some of the talks about GraalVM, and if you haven't ever attended, there's one talk from Alina tomorrow, so please do attend that. But I'm going to give you a super lightning fast introduction to that. The way it works essentially is that it doesn't just do a static analysis of your code in order to understand what code is reachable while compiling. It actually runs your code at build time, especially initializers, so that it can realize what code is reachable even at runtime. And by running this code at build time, it is able to take a snapshot of the heap and put it inside, put it somewhere, actually put it inside a section of your binary, so that when you execute your binary, it will reload that part of the heap immediately without having to execute all the initializers. So it does this in a loop, in order to resolve all of these dependencies. And then that's how you discover all the code that is really necessary, to the point that you can also discard some code. For instance, if you have some code that is only run at load time, such as configuration files, like loading configuration files, potentially you can drop all of the library code that does loading of those config files, because they won't be reloaded at runtime, maybe, right? And that reduces the surface of your executable. So why did I mention this? So essentially what we're doing here, we're moving to preload, pre-initialization files that happens before runtime, some of the logic that originally was happening at runtime. And so you would shrink, essentially, the runtime, the boot time, and move some of that processing at build time. And that's how you can further shrink the executables that you generate. Another thing that is different in native land is how you handle memory. So on the JDK, we have a memory manager, we have a garbage collector that does stuff, so allocates and deallocates memory. So how do you do that when you are compiling a binary? Well, you have to ship your memory allocator. So let's say I want to allocate an array of 8 bytes. So I reserve that memory. Actually, these are 9 cells. This is an abstraction over memory. Let's say that every cell is a byte. I reserve 9 bytes. Why 9? Well, because 8 bytes are for the space of my array, 0 from 7, 0, 1, 7 bytes, okay? And then I'm going to put in the header the number of bytes that follow, so that I know how much space I'm going to use there. So it's 9 bytes, 1 for the count, and 8 for the actual contents of my array. It's just a way to represent an array. There could be others. This is mine, okay? And then you can take, in your linear memory space, in your byte array, you can take an index to this memory and say, at index 0, there's my first element. And that's essentially a pointer. So this is how you do it in linear memory. In WebAssembly, that's essentially the same way you do it in some way or another in native memory. Now, if you want to allocate more memory because you want to allocate another array, that's just the same. You move the index, your pointer, to the next element, and so on and so forth. So, and essentially you use the same strategy whether you're writing an array of bytes. If you're writing an array of integers, the only difference is that an integer takes 4 bytes, so you will have to write it somehow in those cells. If you're writing structured data, let's say you're writing a record, a point of x and y, where x and y are integers, same thing. You're going to serialize these integers into this linear memory space. Somehow, that's not exactly how native memory works, but it's a model for you to understand. And if you want to write an array of points, you write the count, and then you write every point as a pair of integers. That's pretty much how it would work, more or less. Now, as long as you continue to allocate memory, everything goes fine. But as long as you start to finish the space, you probably wanted to deallocate memory. And as you deallocate memory, you will create spaces between the data. So you have to keep track of those spaces so you can reallocate data in the available space, and your memory might become fragmented. So compilers must ship a memory allocator in the generated binary, and this memory allocator might be as fancy as you want. If it's super fancy, we call that a garbage collector. The garbage collector is essentially memory allocator and deallocator, and it does that every once in a while automatically without you realizing, but it's a memory allocator essentially. Yeah, so Java and Go, when they're compiled to native or WebAssembly, they need to ship their own memory allocator, so they're garbage collector. If you want to buy this book, it's on Amazon. It's about garbage collectors. So we were trying to answer the question, can you write software extensions in Java and Go? And essentially, can you write WebAssembly in Java and Go? So yes, you can do it. But you have to manage your own memory. But yeah, you can do it. So I mentioned already that Go provides this flavor. There's this flavor of the Go language called TinyGo, but the Go compiler also is able to produce binaries. But the binaries that it produces are traditionally are a little bit larger than the TinyGo compiler. This is recent. They support running outside the browser with this WASI P1 target, but WebAssembly was a target for a long time. It's just that it used to be targeting just browsers. So the Go compiler supported that for quite a long time. TinyGo started supporting running outside the browser for quite a while. And the difference is in the size of the executables. Now, what are the differences? essentially, TinyGo makes different trade-offs when it comes to compiling Go into an executable. So in some ways, sometimes the semantics are not 100% the same of the original Go compiler. That's why the Go compiler produces larger binary, because it preserves the same semantics that it usually has. Now, we could argue that, in fact, also GraalVM native binaries do not exactly preserve the behavior of a JDK. And that's why some people argue, if you recall I mentioned this earlier, that a GraalVM native image is not really a JDK. In some ways they are right. You cannot do unrestricted class loading. You cannot do unrestricted reflection. If you're a little bit familiar, at least with native image, you have heard about the closed word assumption. It's just a way to make strong assumptions about the way code is compiled so that you can produce essentially smaller and faster binaries. So I wanted to mention GraalVM native image in the context of WebAssembly and not just native execution, because they mentioned this in a blog post of theirs when they introduced support for RISC-V. The way they did it was by using, again, LLVM as a toolchain. So potentially, they also mentioned that the same approach could be used for running Java and, in general, bytecode, Java bytecode on WebAssembly. But this is still not done, not ready. There is, I mentioned already that the way WebAssembly generally behaves is as a native target, in that you have to allocate and deallocate memory explicitly. But there's a new specification that is now part of WebAssembly that is called WASM-GC, which allows you to describe objects and let the runtime manage them, just like you usually do in Java bytecode. That's called WASM-GC, and there is already support for this in browsers, not outside the browsers. But if you're interested, Kotlin has a great support for it. So it's interesting if you're a Kotlin developer, or if you're interested in Kotlin, that's a great thing to try. And also Java has sort of support for it. Google is using it for their products through Jekyll, J2CL. Jekyll is actually an evolution of GWT, Google Web Toolkit. And yeah, it's being used. It originally targeted JavaScript, but it's now supporting also WebAssembly. So, running Java on WASM. Jekyll, Kotlin if you want to do WASM-GC. If you want to write outside the browser, there are a bunch of other possibilities, TVM, bytecoder, cubic.org, but these are super experimental. So, yeah, you can do it, but yeah. I also wanted to mention this project, ShirpJ. This is mostly a proprietary platform, but if you need to run Java software as it is, even Swing application inside the browser without any plugins, this works, and it's pretty impressive. So check it out. Finally, last part of the talk, can you run WASM on Go and Java? So can you host software written by others for WebAssembly, written in TinyGo, written in, I don't know, Rust, inside your applications? And interesting question, why would I do that? So let's talk again about Go and Java. So I mentioned already WASMtime and WASMer and other runtimes that are written using native code. These WebAssembly runtimes can be hosted and embedded inside Java or Go, but they have to be bound through native extensions, as native extensions. And this is important. This is the point that I'm going to try to make. This is just like running native libraries. I wanted to bring this example here. It's kind of famous if you're familiar with that specific domain. This is one of the most famous, not unknown libraries of the Java space. It's called netlibjava, and it's the basis, or at least it used to be the basis for Apache Spark and other platform that did a lot of numeric analysis. netlibjava is essentially a recompilation of some super old Fortran libraries. They're also the basis for NumPy and other frameworks for doing numerical analysis. They're pretty much everywhere, but you might not realize it unless you work in that domain. And they're only available as native libraries, so you have to rely on the support of someone to actually run them. So in this case, they were supporting macOS, but only on x86. So notably, there's no support for Apple Silicon. So if you have one of the newer Apple CPUs, you have worse support. I'm going to get back to this in a minute. So in general, the problem with FFI or foreign function interface is that when you want to interface a runtime that is not natively designed to work as it is with native code, you have to jump through some hoops. And this is normal. This is true for any language that is not designed to do that. So Rust, C, and Zig, and other languages like those are able to interoperate in a pretty seamless way with C code because they're designed to be able to do that. But if you want to link Java against a native library, you have to use JNI. Sooner or later, well, you probably can already use some flavor of Panama already, but that's just a better API. The same restrictions will actually apply. And the same is true for Go. That's called CGo, and it's essentially their version of JNI. Much more convenient to use, but they actually have kind of the same restrictions. So these restrictions are essentially that you have portability issues. Now, you used to be able to compile to every platform and run on every platform. You were both for Go. In the case of Go, you could compile to that platform. In the case of Java, you just compile to bytecode and use it on any JDK that it's available. You have tooling issues. Now the native code is a black box. You cannot use your normal debugger to debug that code. You have runtime issues because native threads and virtual threads do not really play nicely with each other. So, and obviously you could have performance issues because crossing the FFI boundaries has a cost. You have safety issues because if you corrupt memory native land, you corrupt memory also of the Go or Java runtime. So it's a bunch of issues, and sometimes you don't have a choice, but you would like to avoid that. So if you want to do software extensions in Go, for instance, I mentioned already that software that's produced through Go, it's a static binary. So essentially doing dynamic code loading is not really something that you normally do in Go. And kind of goes against one of the best features of Go, which is creating a self-contained binary. So you lose cross-compilation. If you do dynamic loading on native executables, you lose cross-compilation. You have problems with Go routines. So how do you do software extensions in Go? There's a framework that's called Go plugin that allows you to do that, but it's very limited. It only works on a bunch of platforms, so you don't really want to do that. You could provide your end users with a scripting environment, but if you want to avoid using native extensions, then also that scripting environment must be written in pure Go. So you must find a scripting language that is written in Go, and there are not many of those. Or you can resort to native extensions. This is also true for WebAssembly runtimes. So let's say that you want to run Rust code inside Go or Zig code inside Go. This is how the memory space would look. It's mixed between Go and Rust and Zig. So they can interfere with each other. If Zig or Rust corrupts the memory of the Go host, you can tear down the entire Go host. And that's not definitely what you want to do, especially if this foreign code comes from your end users. So instead, if you can host a WebAssembly runtime, the WebAssembly runtime confines the execution, confines the boundaries of the memory that these executables are able to access, and you won't be able to corrupt the memory of the host. The only problem is, if your WebAssembly runtime is a native executable, then you still have this issue. Keep this in mind. What about software extensions in Java? Well, in Java, we mentioned that dynamic loading is a defining feature of the JDK, right? But then if you compile to native, you lose that ability, right? So another thing that you can do is use a scripting language that developed in Java, just like we mentioned in Go. And obviously, as a last resort, there's native extensions. So as I mentioned, dynamic loading is essential, so that's one feature that you could use. However, Security Manager has been deprecated and it's always been finicky to work with. And besides, there's no real sandboxing, right? If you allocate a bunch of objects, there's no real control over memory consumption, over CPU usage. It will be able to do pretty much whatever it wants. So you can do that, but especially if you want to run foreign code, it's not great. So scripting language, those give you much more control. There's not a lot of scripting language. There's a bunch of scripting languages, but if you want to run any code from any language, well, the choice is more limited. You have some choices, and especially if you're able to run GraalVM, then you have even more choices. So that's one way to do it, definitely. However, sometimes native extensions are the only solution, especially if you want to run stuff that is only available as a native extension. I admit that this is a very particular and special use case, but as I mentioned, so this library, even though it's a very special case, it's actually used in a lot of places, and you might be familiar with this XKCD comic. This is exactly what was happening, and that's why eventually the maintainer burned out and decided to give up. No, fuck it. So we are here in the same kind of situation with Java. If you want to run code that is written in a foreign language and you want to run it as a native code, you will get the same situation of mixed memory. So how can you do and solve this problem? Again, another solution might be running through WebAssembly. Are there any WebAssembly runtimes for Java? Well, some people are starting to call these language native runtimes. I would say the first was Waziro. Waziro is a WebAssembly runtime that is written entirely in pure Go and plays some Jedi tricks in order to be able to compile code into memory, into native code, and provide an efficient runtime, even in a static native Go binary. So it's pretty cool, and it's pretty fun to work at. But there's also a runtime for WebAssembly in pure Java that's called Chicory. So you might be interested in that. Why would you want to do that? You can provide your end users the capability to write using any language that they want, and you can also use it to do FFI. So if you have some native libraries that you need to use for some reason, one way could be to use WebAssembly. That's weird. Why would you do that? So I mentioned already Waziro. Waziro, it comes with an interpreter that runs on any platform, but we also have a compiler that runs on specific platforms. Those that are most available, MET64, ARM64, and then major operating system. So Chicory, it's a pure Java runtime. It's an interpreter, so it's not super fast, but there's planned work on an AOT bytecode transformation in order to run as fast as the JVM. So as I mentioned, why would you run native code on top of a JVM? Why would you do that? Well, this is an interesting demo just to show you that it actually works. You can run Doom, translated to WebAssembly. And this was originally developed for another runtime, which is GraalVM. So it was developed for Graal. But my friend Andrea, who's working on it, actually ported it to Chicory. And as I mentioned, GraalVM, it's another implementation that runs on top of GraalVM and Truffle. So here's another WebAssembly runtime for you if you're interested. So use cases. People can run foreign code inside their Java application. For instance, another friend of mine, Luca, brought this to Apache Camel to be able to run WebAssembly transformations like they did for Red Panda. So Camel and Kafka, you can now run WebAssembly transformation in the core, or Kafka Connect outside the core. Another use case is foreign function interface. This is some crazy user of Waziro that used WebAssembly to port a Rust library to Go, because that was just the best implementation. And there are a bunch of use cases. A bunch of users are actually doing this. It's weird. Yes, it is. But it's not so weird as you would think. In fact, JRuby has recently embraced Chicory as a fallback for the parser that they're shipping with the new versions, the parser for Ruby. You might not know this, but the Ruby parser is a nightmare, and every time they release a new version of Ruby, they update it. And the only way to parse Ruby is essentially to run the C parser. Obviously, running C on top of the JVM is not convenient because you have all of those limitations. So the idea for them was, well, we could build native binaries so they will run super fast on all the platforms that you support, and then we ship WebAssembly binary as a fallback for the platforms that we do not yet support. So people have a reasonable fallback in order to support all the platforms where people might want to run JRuby. So here's the use case. Conclusions. The JVM and the Go runtime are much more alike than you might think. Compiling Java bytecode to WASM needs similar processing as GraalVM Native Image, and hopefully you learned something about both today. WebAssembly to me is pretty cool. Check out Chicory, and if you want to learn more, or you want to just have a refresh, just to reread what I said in this talk, you can also check out this blog post that I wrote a few months ago. This is essentially what the talk is based on, and that was it. Thank you.